For coming, so again, like last week, we need to write the list of names of the participants. So the paper will go through. Right. So today,
this is a joint work with Ben Silikov and István Toma. And it's about small subgraphs with large average degree. So it will be about, we prescribe some average degree that we want to achieve in our subgraph, and we want our subgraph to have as few vertices as possible. So how small such a subgraph can we find? Okay, so the motivation comes from an important problem in theoretical computer science, which is the densest k-subgraph problem. This problem asks for an algorithm which finds the subgraph on k vertices which has the most edges. So we want an algorithm, efficient algorithm, finding densest subgraph of a given graph on k vertices. And this is an important and difficult problem. It's known to be NP hard, and it's also known that there is no polynomial time algorithm which obtains a good approximation under some complexity theoretic assumptions, and the best known polynomial algorithm achieves an approximation with this error term. So the subgraph that it finds may not be the densest one, and it may have the density may differ from the real densest one by a factor n quarter. So it's quite a large gap still. And this problem motivated.
wait, n is what? N is number of vertices?
N is the number of vertices. Number of vertices in the host graph. Yeah, please do ask a question.
I mean, the thing is that if you assume n is huge, then the average degree, the density of the k-vertex subgraph is the most.
So k is not a fixed number here.
Oh, k is not fixed.
So yeah.
Right.
Otherwise,
Yeah.
Otherwise, you cannot have this sort of gap. But k there can be a function of n. So an extremal question was asked by Feige and Wagner, and that will be the topic of our talk. So problem of Feige and Wagner 2016 is that given you know the number of vertices and edges in your graph, how small subgraph can you find which has a certain average degree? So given some parameters S, D, and N, what is the smallest T such that every graph which has every graph with n vertices and average degree D, at least D, say, contains a subgraph of average degree at least S on at most T vertices. So let's think about this a little bit. So we have some parameters, and S will be a constant throughout the talk. So the problem does make sense even when S is not constant, but Feige and Wagner were mostly interested in this case. So S is a constant, and that's the average degree in our subgraph that we want to guarantee. However, D and N are not constants. I mean, N is obviously the number of vertices, and D can grow with N. So note that the assumption that D is at least S guarantees that there is at least some subgraph which has average degree at least S. You can take the whole graph, and the whole graph has average degree D, so it has average degree at least S. But what we're interested in is finding the smallest subgraph which has average degree at least S. And ideally we want an answer to this question in terms of these parameters, assuming that S is constant. So there is a special case, which is the case S equals 2. That has to be treated separately. So when S is 2, you're looking for a subgraph with average degree at least 2. Now, any such subgraph must contain a cycle. But conversely, any cycle has average degree at least 2. So in fact, you just want to know what's the length of the shortest. What's the length of the shortest cycle? So this is a famous problem. It's called the girth problem. Girth problem asks, given your average degree, what's the largest possible girth? And it's known that the answer is of the order logarithm n, where the logarithm is base d minus 1. So this is known. This is the length. This is the length that you can guarantee. But we don't know what kind of absolute constant comes here, and that's an important open problem. But as we will see, the S greater than 2 cases, the answer will be very different. So before I turn to the answer, let me take one example to demonstrate the flavor of this problem. And my example will be S equals 4. And D equals n to the 1/4. That's just friendly looking numbers. So we are given a graph with n vertices, average degree n to the 1/4. We want to understand how small subgraph we can find which has average degree at least 4. So what are some methods for finding a subgraph with large average degree? So perhaps the most natural method is to try to use random subgraphs. So what happens if we take here is our host graph G, and we take a random subgraph on T vertices? What kind of average degree do we think it will have? And the average degree in this subgraph H will scale with the size of the number of vertices in the H. So average degree expected average degree in H will be T over N times the average degree in G, which was D. And that's T over n to the 3/4. So in order to guarantee an average degree that's at least 1 even, we need, with this method, we need T to be roughly at least n to the 3/4. If you choose a random subgraph with less than n to the 3/4 vertices, your average degree will be very likely very small. So this is what this random subgraph method gives, but as we will see, this is not optimal, and what we will show is that in this particular example, you can even take T to be n to the 1/2 plus little o1. So as a special case of our main theorem for this restricted to these parameters, we'll say that you can find a good subgraph on only n to the 1/2 plus little o1 versus which still has average degree at least 4. It will not be a typical subgraph, but there will be such a subgraph. Okay, so now let me state the straightforward lower bound for this problem. So it was observed by Feige and Wagner when they posed this question that random graphs give some reasonable lower bound. Of the form constant n times d to the minus s over s minus 2. So this formula will be relatively important throughout the talk, because this will turn out to be the answer. So that we don't really care about the constant here, but the important thing is that it's n times d to the minus s over s minus 2. Obviously, you can see that s equals 2 case is going to be very different, but when s is greater than 2, then this is well defined. So this means that there is a graph, and it's a random graph, in which every subgraph with average degree at least s has at least this many vertices. And their conjecture was that this is optimal up to some polylogarithmic factors. And our first main result is that we prove this conjecture with a slightly better error term, in fact. So, together with any pseudocarbon we proved that TSDN is at most n times d to the minus s over s minus 2 times, and the error term is only logarithmic in d, logarithmic in d instead of n, which is obviously better when d is quite small. I should mention that you might wonder why this logarithm is needed. It actually is needed when d is very close. I should say what range this is valid for. So I should say that this is for d at most n to the s minus 2 over s. D at least s. If d is bigger than s minus 2 over s, then this bound becomes smaller than 1, and you certainly can't get a bound that's smaller than 1, because a subgraph with 0 vertices will not have average degree at least s. So everywhere, if I forget to write, it is understood that d has to be at most n to the s minus 2 over s. And what I wanted to say is that if d is around n to the s minus 2 over s, then you do need this logarithmic. You do need this logarithmic term. So that's actually needed. So we proved that this bound. We wrote a conjecture with a slightly stronger bound, and it's natural to wonder what happens when your edge, where your average degree is a little bit bigger than this. So let's say you are above this n to the s minus 2 over s average degree. So you could use this theorem with d set to n to the s minus 2 over s, but then the bound that you get on t is logarithmic. So what if you want to find a constant size, a bounded size subgraph with large average degree? So what if you want a bounded size subgraph? You can't use this theorem, but as we'll see, we can still say something. In fact, something optimal. So it was observed that the random graphs show that for any fixed t and s, so now you fix s, the average degree you want to achieve, and you fix t, the size of the subgraph that you are okay to use. For every fixed s and t, there exists some epsilon such that there are n vertex graphs with average degree at least n to the 1 minus, well, I would say s minus 2 over s plus epsilon without a subgraph with average degree at least s on t vertices. So what it says is that no matter what your t is, if I choose epsilon small enough, then I can come up with a graph which has average degree this, and it will not contain a small enough subgraph with average degree at least s. And that suggests very naturally the following conjecture that was asked by Verstraëte. Conjecture is that for every s and epsilon, there exists some t such that if G is an n-vertex graph with average degree at least n to the s minus 2 over s plus epsilon, then it contains a subgraph with average degree at least s on at most t vertices. That is, we can find these bounded subgraphs. It just depends. It's just how small the subgraph is has to depend on this epsilon. Okay, and our second main result is the proof of this conjecture. So conjecture is true. Okay. So now what I'll do the rest of the talk is I'll talk about the proof of the first main result. I'll not talk about, actually the proof of the second main result is quite similar, but I just want to focus on the first one for simplicity. So I'll put this up. Actually, where? Ah, it's there. Okay, so there is the result that I want to prove. Okay, so let's see. What I will do is I will first start with a sketch, then I'll explain where in that sketch I have cheated. There will be 2 or 3 places where I'll cheat, and then I'll explain how we can make those arguments more rigorous.
So you have any intuition that you have this exponent s over s minus 2?
Yes, there is. I will start with. I will start with that. I'll start with giving that intuition. Any questions so far? Okay. So let's see what's the broad strategy. So the strategy, how to find. So I need to find small, dense subgraph. dense in the sense that its average degree is S, and small in the sense that it has at most this many vertices. So what I will do is take many copies of some tree, some very large tree, so it's not a bounded size tree at all, with the same set of leaves. So we have this hot graph G, in which we want to find a small subgraph, and I fixed some tree T, and I want to find lots of copies of that tree in my graph A, in my graph G, which share the same set of leaves. And then I'm kind of hoping that when I take the union of all these trees, it will be fairly small and fairly dense. Of course, that depends on my choice. So let's see what would be a sensible choice for T, and how many copies I will try to glue together. So T will be a tree with roughly T vertices, where T is this target size that I want to achieve. I will completely ignore, so from now on I will ignore logarithmic terms, and I will not have time to make a super rigorous argument, but if we ignore logarithmic terms here and there, it will be mostly okay. So this is the size that I'm aiming for. So this is exactly the size of my tree, and then my strategy will be to glue together not too many of these trees. And if I glue together, say, a logarithmic number of these trees, then the size of the union will be just a logarithm times the size of an individual tree. And since I allow this logarithmic error term, the union will be small. So the small part is automatically satisfied with this choice if the tree is not too big itself. So what I need to make sure is that it's going to be dense enough. So this is where I need to specify another condition for the tree, which is that the number of leaves should be L equals S minus 2 over S times T. So this is basically so far all I need from my tree. I told you how many vertices it should have, and I told you how many leaves it should have. The number of leaves is some constant proportion of the number of vertices. Definitely such trees exist. And that will already be enough to intuitively see why this n times d to the minus s over s minus 2 is the right answer. Okay, why did I choose this many leaves? Well, let's see what happens if I start gluing those trees together. So here's my first copy of the tree with some set of leaves L. And then I glue a second copy and a third copy, and so on. What happens when I add a new copy of the tree T to this picture? How many new edges do I get? Well, it kind of depends on whether the new tree is edge disjoint from the previous trees or not. But simplifying assumption number 1, and that's the first place where I cheat is that assume the trees I found are for some reason edge disjoint. You see that if they are not edge disjoint, that's a bit of a problem because I don't get as many edges in the union as I expect. But let's assume that they are edge disjoint. So every T is a tree with roughly T vertices, so roughly T leaves. So every new tree, every new copy adds roughly T new edges to this union of copies of T. And how many new vertices do I get? Well, it is assumed that the set of leaves is the same. So the leaves are not new, only the non-leaves are new. So every new copy adds T minus L, which is 2 over S times T new vertices. So these are the two crucial things for this process. Every time I get T new edges and 2 over S times T new vertices. Now what if I do this for very long, say logarithmic steps, then it will not really matter that I started with some set of size L. So yeah, when there are no trees yet, just a set of leaves, then my number of edges is 0 and the number of vertices is pretty large. But when I keep adding this, eventually I'll end up with some number of V vertices and roughly 2 over S times V, S over 2 times V edges. Because you see that for every new vertex, I add S over 2 new edge. So I will end up with V vertices and roughly S over 2 times V edges. And if you think about the edge density of such a graph, the average degree in such a graph is S. So I will end up with average degree at least S if I do this long enough. Of course, I cheated a little bit because you will not get average degree precisely as you will be a little smaller, but you will be close. Now, what do I need to check? Well, it was crucial for this argument that the trees, that I have several copies of trees with the same set of leaves. Because if I have just one copy of the tree with a given set of leaves, then I can't do this. I can't add several copies of the same tree with the same set of leaves. So I need to check that there are many copies of T with the same set of leaves. So I need an estimate for the number of copies of this tree overall in the graph. What do I know about the tree? I know that it has roughly T vertices. So imagine that it was a random graph. Imagine that the host graph G was a random graph with average degree D. Then the number of copies of T would be roughly D to the T. You need to choose
I mean, you could maybe be a little bit more precise and say n times d to the t. You need to choose the first vertex of the tree, and then for every new edge, you have basically d choices in your random graph with average degree d. So this is the number of copies of the tree you get in a random graph. I need to check that for a set of leaves, this gives enough copies. So how many possible set of leaves are there? So set of possible, well, number of possible sets of L leaves is obviously n choose L. There are n choose L ways to choose n vertices, L vertices. So what I need to check is that this number of copies for the tree is much bigger than this number of possible choices for the L leaves, because then by pigeonhole principle, I'm obviously fine. So check, and I will do it quickly, that this n times d to the t is much larger than n choose L. Okay, let's do some list computation. So n choose L is roughly n e over L to the L. So L is up to a constant, is just t, and t is n times d to the minus s over s minus 2. So this is some constant times d to the s over s minus 2 times L raised to the power L, which is constant d s over s minus 2 s minus 2 over s t, which is a constant, doesn't really matter, and you get roughly d to the t. You get roughly d to the t. And that's what roughly your number of trees was. So to answer your question earlier, this computation justifies why this s over s minus t will be the right exponent intuitively. So this is basically intuitively how the proof goes. So let me address a couple of issues with this catch. So the first one, which I've already tried to stress, is that it was assumed in this sketch that the trees that we glue together are edge disjoint, but that doesn't need to be the case in general. So why is that a problem? Well, the following thing can happen. So you could say that if the trees are not edge disjoint, that means that they are not vertex disjoint either. So maybe, although the number of edges in the union will be smaller, the number of vertices will also be smaller, so maybe the average degree is still okay. But the following example shows that that's not the case. So here's the example. Let's say that this is the tree. That you take. And then you take another copy of the same tree, which is the same, except for the top vertex, which is different. And then you take yet another copy, which is again the same, except the top vertex is different. And so on. So when you glue the two trees together, they are mostly the same, except the top vertices are always different. Now, how many new edges do you get when you add a new tree? You get just 2 new edges, because only the top vertex gives new edges. So you get 2 new edges, and one new vertex for every new tree. That means you get a ratio 2/1. But in the sketch we assume that the trees are edge disjoint, and if they were edge disjoint, you would get 1, 2, 3, 4, 5, 6, 7, 8 new edges and 3 new vertices. So in the sketch, we had this, and the computation worked with these numbers. It will not work with this number, because in a union, your average degree will be too small, because instead of getting new edges with the ratio 8/3, you get new edges with ratio 2/1. So if you use this tree, this argument will not work, unless you somehow make sure that your trees are always edge disjoint. So it turns out, I mean, you could try to argue that you can always find trees to be edge disjoint, but that's not the path we will take. What we will do is just restrict our attention to specific trees for which this does not happen. This issue that's on the picture will not happen. And they will be so-called balanced trees. So the way to fix it is we use balanced trees. So the problem with this tree was that the top part was too sparse. This vertex had only 2 neighbors, and the local density there at the top vertex was much smaller than the global density of this tree. So the balanced tree will be a tree which is not like that, which is nicer. So it's a definition that is due to Book and Conlon in the context of rational Turan exponents. So their definition is the following. So if T is a tree and S is a set of non-leaves, so L is the set of leaves, S is some set of non-leaves, then the local density at S is the number of edges leaving S divided by the size of S. So ES is the number of edges with at least one endpoint in S. So your local density of this tree with respect to this subset S is the number of edges that are incident to this set normalized with the size of the set. So roughly speaking, it's the average degree of vertices in S in some sense. And the overall density is just this local density for the entire set of non-leaves. And we call T balanced if the local density is bigger than the global density for every S. So what it means is that, I mean, here in this example, if your S is the singleton consisting of this top vertex, then the local density at S is just 2/1, 2 new edges, 1 new vertex, whereas the global density is 8/3. So it's not balanced because for that singleton S it violates this balanceness condition. But if you add this balanceness condition, that's you can check that it's precisely what ensures that the problem I sketched there will not happen. So every time you add, even if your new tree overlaps with the previous stuff, you'll get new edges at least at the required rate. Maybe more, maybe a better rate, but at least the required rate. So these are very cool trees, and fortunately they exist for every T and L. So it doesn't matter what, I mean, we already specified a number of vertices and number of leaves that we want, but that's not a problem because Book and Conlon have already shown that balanced trees with T vertices and L leaves exist for any reasonable T and L. By reasonable I mean number of leaves should be less than the number of vertices. Cool. So that's good. So that fixes the first problem. It doesn't matter whether or not the union is disjoint union or not. The second.
How it looks like a balanced tree?
It's they're caterpillars. So you take a path, and then you add the legs in some balanced manner. So there is a specific description, but roughly speaking, for every vertex, you add either k or k plus 1 leaves. So what would ruin the balancedness if here you added a million and here you just added 1? That would obviously, it looks very unbalanced. But if you do it in a reasonable way, that you add r or r plus 1 basically everywhere, then it's roughly speaking that will ensure the balancedness. Okay. So the second problem was that we assumed, so we used some lower bound on the number of copies of T in our graph, which we did not justify. We said that in a random graph, so we said in a random graph we have d to the t copies of our t vertex tree, but in a non-random graph it's not true that this lower bound holds. And you can easily construct an example. You can take disjoint cliques of size roughly d. You take a disjoint union of kds, then the average degree will be roughly d, but you might not have a single copy of t in this graph, because if t is bigger than d, which is absolutely possible, I mean t is given by this formula, may or may not be bigger than t. But if t is bigger than d, then you can't fit a t in a single box. So you will not find any copy of this tree, and that's a problem, because our main strategy was to find lots of trees and glue them together. But if you can't find any, that's a problem. So the thing to notice here is that this graph, this union of cliques, is really not a graph that's problematic for us, because it has these relatively small, extremely dense subgraphs. So kind of if this really happens, that d is less than t, and you have these very dense sets, you're already done. Because you can take sets of size less than t, you can just take a huge clique. Not so huge clique. So to make this dichotomy precise, we use notion of expansion. So G is an mk expander if for every set of vertices with size at most m, the expansion is at least k, namely the union, sorry, the neighborhood of S is at least k times S. And this stands for the set of neighbors of some V in S. It's not a common neighborhood, it's just neighbor to at least one vertex in S. So this is an expander. And now either G is not an not a T, let's say Tx expander, what does it mean? It means that there is a set S of size at least T which does not expand, which means that the entire neighborhood is only a bit larger than S. So you take this relatively small set S and you take its neighborhood, it's still relatively small, but it contains every single edge leaving S. So if S had some reasonable minimum degree, then this contains a very large multiple of the size of S edges. So let's say the graph had minimum degree delta, then this union contains delta times S edges, because it contains every edge leaving S, every edge leaving S. Yes. If you contain this many edges, but the size of the union is only k times S, so the average degree will be pretty large. It will be much larger than S if delta is a large minimum degree. So if it doesn't expand, then you can zoom in where it doesn't expand and use that set basically as your small set of large average degree. And if it does expand, then we can use a theorem of Friedman and Pippenger that tells you that expanders contain trees. So if G is an MK expander, then it contains every tree with at most m over 2 vertices and max degree at most k minus 1. So that's really good for us, because that means that if we do have a TS expander, then we can find our copy of T in this graph. And in fact, if we slightly modify this argument, we can find not just one copy of T, but the right number of copies, as in the random graph. So with distinguishing the cases whether or not this is an expander, we get we either are done directly, or we have enough trees and then we can run the previous argument. So let me just finish by mentioning two open problems. So the first open problem is actually an even older problem than this Feige and Wagner. It's due to Erdős, Faudré, Rousseau, and shelp, and it's asking what about minimum degree S subgraphs. So in this work that I did with Ben and Istvan, we answered how small a subgraph can be found with given average degree. But what if we want to find a small subgraph with large minimum degree? That is a different problem. And although we could find a subgraph with average degree at least 2s, and in it a subgraph with minimum degree s, that would not give the optimal answer, because we think that the optimal answer is still the same. We don't know that, but we think that the optimal answer is still this. And you can even ask for regular. What about S-regular subgraphs? We still think, we don't have a lot of evidence, but we still think that the answer might be the same. So the same number of vertices, on the same number of vertices you can find even an S-regular subgraph. So some evidence you might have for this is that you can consider the other problem that I mentioned in the beginning about bounded degree, bounded size subgraphs. There, it was assumed that it was shown that we need average degree this to guarantee a bounded size subgraph with average degree at least s. But in this situation, it is known that this is enough to contain an S-regular bounded size subgraph if S is 3 or even. And it's very likely that the same thing holds for odd values of S, but that is not known. And that's all I wanted to say. Thank you for your attention.
Okay, any questions?
Yes.
What is the best known exponent for the minimum degree problem?
The best known, well, I think for that problem there's nothing written, but other than what comes out of our method. So what we can do is find subgraph with average degree 2s. So there you would need obviously this. And in an average degree 2s subgraph you can find minimum degree s subgraph. So the short answer to your question is this is the best known, but it's very clear that you can improve that. Even I think by analyzing our proof, you'll improve it. But our proof will not give the tight answer, because if you think about it, what we do, we take these unions of these trees, and they will be very much non-regular, because the leaves will have very large degrees, but the remaining vertices will have degree less than s. So it will not have minimum degree s. Thank you.
Other questions? I'm wondering about the highly connected subgraph. Can you find a small subgraph which is highly connected? Because people in network science
Yeah.
will talk about the HCS, highly
Right.
connected subgraph.
Yeah, that's a good question. So you would, I mean, so some sort of natural analog of this problem would be you start with a highly connected host graph. What's the smallest subgraph that's you can guarantee that's still highly connected? Some problem like this
Mhm.
could be interesting. Yes, we have not studied that, but that sounds natural. Yes. Yeah, you can. I guess you can very much replace. I mean, we work with average degree. So you start with large average degree, and you want small subgraph with small average degree. But you can replace it average degree with other notions, and it all falls within this local global principle that if you assume something about all the local sets in the graphs, then you can deduce something from in global sense, and that applies equally in other settings for sure. Yes.
There are questions? So if not, let's thank the speaker.